Hello friends, so we will take the last lecture on system of linear equation. In that our question is solve following system by any method. Question number 5, solve by any method, either Gauss elimination or Gauss-Jordan elimination, any method. In that first example, or I will take B from that, x plus 3y minus 2z is equal to 0. 2x minus 3y plus z is equal to 0. And last equation is 3x minus 2y plus 2z is equal to 0. So, this is the homogeneous system of three equations in three unknowns. And homogeneous system is always consistent as it has trivial solution, that is x is equal to 0, y equal to 0 and z equal to 0 satisfy all equations simultaneously. So, we will only take coefficient matrix of system. Argumental matrix is not necessary, because if I take the constant 0 0 0, if I apply any row operations on that constants 0 remains zeros by any elementary row operation, and that's why it is not necessary to write that constant column vector 0. So coefficient matrix of system is coefficient matrix of system is A is equal to, we will just take A. What is A here? 1, 3 minus 2, 2 minus 3, 1, 3 minus 2, 2. And we apply row operations on this. As usual, R2 minus 2R1 and R3 minus 3R1. This gives us equivalent matrix 1, 3 minus 2, 2 minus 2 gives us 0, minus 3, then minus 6, that will be minus 9, right? 1 plus 4, 5, then 3 minus 3, 0, then minus 2, minus 9, minus 2, minus 9. Okay, so that will be minus 11, and then lastly 2 plus 6, 8. We will get this one. Now we have to obtain 1 in this position. So what we will do here, we will apply the operation R2 minus R3. R2 minus R3. What R2 minus R3 gives us? R2 minus R3 gives us, this is equivalent to 1, 3 minus 2, 0, minus 9 plus 11, that is 2, then 5 minus 8, that is minus 3. 5 minus 8, 0 minus 11, 8. And then we will try to obtain 1 here by using operation R2, 6 times R2 plus R1, R3 gives us 1 there. 1, 3, 2, 0, 12 minus 11, 1. Then minus 18 plus 8, minus 10. Minus 18 plus 8, 10, 0, minus 11 and 8. and then last one R3 plus 11 R2 gives us, this is equivalent to 1 3 2, 0 1 minus 10, 0 0, and 8 minus 110, right. This is 8 and minus 110. So what that gives us? 8 minus 110 gives us minus 102. Minus 101 minute. So 6R2 minus 18 plus 8, that should be minus 10. Is it clear? And then it will become minus 102, and lastly minus 1 upon 102 R3. This gives us 13201 minus 10001. So therefore reduced system is x plus 3y plus 2z is 0, y minus 10z is 0, and z is 0. So by back substitution or Gauss elimination method, solution is z0, then putting z0 here, y0, putting yz0 will get x0. So that is the solution of system. Is it clear? We'll take one more example. Next example, 3x1 plus x2 plus x3 plus x4 is 0, 5x1 minus x2 plus x3 minus x4 is 0. Now for this, coefficient matrix A equal to 3, 5, 1, minus 1, 1, 1, 1, minus 1. We have to obtain 1 in first position. So how to obtain that? R1, 2 R1 minus R2. 6 minus 5. This gives us 6 minus 5, 1. Then 2 plus 1, 3. 2 plus 1, 3. 2 minus 1, 1. Then 2 plus 1, 3. 5 minus 1, 1 minus 1. Then applying the operations, which operations will apply here? R2 minus 5 R1. This gives us 1, 3, 1, 3. 5 minus 5, 0. Then minus 1, minus 15, minus 16. Then 1 minus 5, minus 4, minus 1 minus 15 minus 16. We get this. Then we'll obtain 1 here in 2-2 position. For that we'll apply the operation minus 1 by 16 R2. This gives us 1 3 1 3 0 1, then 4 by 16, that here it will become 1 minus 5, that is minus 4. So 4 by 16, that is 1 by 4, and next one is 1. So this is your row echelon form. This is the row echelon form, right? Again, if you want to obtain, say, row reduced echelon form, I will use R1 minus 3 R2. This gives us 1, 3 minus 3, 0, 1 minus 3 by 4, 1 minus 3 by 4, that is 1 by 4, then 3 minus 3, 0, okay, 0, 1, 1 by 4 and 1. So we'll get this to be row reduced echelon form. From this row reduced echelon form, from this reduced system is x1 plus 1 by 4, x3 is 0, and x2 plus 1 by 4, x3 plus x4 is 0, where x1, x2 are leading variables and x3, x4 are free variables. So we'll assign parametric values to free variables. Substitute x3 is equal to, say, yes, x4 is equal to t. Then x2 is equal to minus 1 by 4 s minus t, and x1 is equal to minus 1 by 4 s. Therefore solution set is minus 1 by 4 s minus 1 by 4 s minus t, s t, st belongs to R. This is your solution set. Now we'll take the next example. We'll take now example number E from that. 2x plus 2y plus 4z is equal to 0. W minus y minus 3z is 0. 2w plus 3x plus y plus z is 0. Minus 2w plus x plus 3y minus 2z is 0. 2, 2, 4, 1 minus 1, minus 3, 2, 3, 1, 1, minus 2, 1, 3, minus 2. So Again, this is a homogeneous system, so it is not necessary to take argumented matrix form. Coefficient matrix of system is A equal to, so it's like WXYZ, WXYZ. What is W column? 0, 1, 2, minus 2. X column 2, 0, 3, 1. Then Z, Y 2, minus 1, 1, 3, 4, minus 3, 1, 2. Let me verify it. 0, 2, 2, 4, 1, 0, minus 1, minus 3, 2, 3, 1, 1, minus 2, 1, 3, 2. 3 minus 2, sorry. So if you make a single mistake, then your answer will not match whatever answer given in the book. So we'll apply, we want 1 in first position, R1, 2, this gives us. And we'll also apply, okay, R4 plus R3, doesn't matter. So that gives us 1, 0, 1, 0, minus 1, minus 3, 0, 2, 2, 4, 0, 2, 2, 4, then 2, 3, 1, 1, 2 plus 2, 2 minus 2, 0, 3 plus 1, 4, 4, and here next one is 1 minus 2, that is minus 1. We get this. Then 1 half R2 and one more operation, R3 minus 2 R1. This gives us 1, 0, minus 1, minus 3, 0, 1, 1, 2, then 2 minus 2, 0, 3 minus 0, 3, 1 plus 2, 3, then 1 plus 6, 1 plus 6, 7, then 0, 4, 4, minus 1. So, by applying 1 half R2, R3 minus 2 R1, we are getting this step. Now, we have to convert this 3 and 4 to 0 by using this leading 1. So, we will apply the operation R3 minus 3 R2 and R4 minus 4 R2. So, R3 minus 3 R2 gives us 3 minus 3 is equal to 0, 3 minus 3 is 0, then 7 minus 6 is 1, then 0 minus 0, 4 minus 4 is 0, 4 minus 4 0, minus 1 minus 8 minus 9. Then this is your leading 1 here. By using this leading 1, okay, so what we have done, firstly, by using this leading 1 now, we have to make a below entry 0. So R4 plus 9 R3 gives us 0 here. So we are getting this one. Now, in this leading 1 column, all remaining entries are zeros. In this column containing leading 1, all the entries are zeros. So this is leading 1, this is leading 1, this is your leading 1. By using this leading 1, we will make above entry 0 to get the row reduced echelon form. This is your just row echelon form. So I will use this one to make above entry 0. So I will apply R1 plus 3 R3 and R2 plus R2 minus 2 R2 operation to get zeros there, and then we will get, this is your row reduced echelon form, 1 0 minus 1 0, 0 1 1 0, 0 0 0 1 and 0. So from this row reduced column formed, column first, second and 4 contain leading ones. Therefore corresponding variables w, x, the y is not leading, z is the leading variable and remaining variable y is free variable. Reduced system is w plus 0x minus y plus 0z. So w minus y is 0. Next one is 0w means not necessarily right, x plus y plus 0z is 0 and lastly z is 0. So your free variable is y, will assign parametric value to y, say t. Then from this x is equal to minus y gives us x is minus t, w is equal to y equal to t. So your solution set become t minus t, t 0, where t is the real number. Thus there are infinitely many solutions for this system. Now we will take the next question. Question number 6 from the book. What is the question 6? Determine the values of a for which determine a for which system has no solution, unique solution, or infinitely many solutions. So you have to find out conditions on A. So in that first one is x plus 2y minus 3z, x plus 2y minus 3z is equal to 4, 3x minus y plus 5z is 2, 4x plus y plus a square minus 14 is equal to a plus 2. So now this is the non-homogeneous system because right hand side equation has some non-zero entries there. So we have to use argumental matrix form. Argumental matrix of system is AB is equal to coefficient of x 1, 3, 4, coefficient of y 2 minus 1, 1, coefficient of z minus 3, 5, a square minus 14. Let me again check whether the signs are correct or not. Yes, that signs are correct. 4, 2, a plus 2. If there is one sign mistake, our answer will become wrong. Now, this is your leading one. Use this leading one to make below entry 0. So, we will apply the operation R2 minus 3R1, R3 minus 4R1. This gives us 1, 2 minus 3, 4 as it is. Then 3 minus 3, 0. Minus 1 minus 6, that is minus 7, then 5 minus plus 3 into 3 9, 5 plus 9 14, and 2 minus 12, that is minus 10. Okay, the next one is 4 minus 4 0. You have to multiply first row by 4 now. 1 minus 4 into 2, 8. So 1 minus 8 is minus 7, right? And then a square minus 14 plus 12. So we'll get a square minus 2. A square minus 2. and a plus 2 minus 4 into 4. 4 4 or 16. So that will become a plus 2 minus 16, a minus 14. Then we will subtract this from this. So R3 minus 7 minus R2, this gives us 1 2 3 minus 3 4, 0 minus 7 14 minus 10, then 0 minus 7 plus 7, a square minus 2 minus 14, a square minus 16, then a minus 14 plus 10, a minus 4. Okay, and minus 1 by 7 R2 gives us 1 2 minus 3 4, 0 1 minus 2, and 10 by 7 0 0, a square minus 16, a minus 4. Okay, case 1, for a equal to 4, a square minus 16 is 0, a minus 4 is also 0, and therefore from R, rank A is equal to rank AB is equal to 2 less than number of variables is equal to 3. Therefore system has infinite many solutions. Infinitely solutions if A is equal to 4. A equal to 4. Now case 2, if A is equal to minus 4, then a square minus 4 16 is 0, but a minus 4 will become minus 8 not equal to 0, and therefore from R, rank A is equal to 2 less than rank AB is 3, and therefore system has no solution for A is equal to minus 4. Okay, case 3, if A is not equal to plus minus 4, then a square minus 16 is not 0, implies rank A is equal to rank AB is equal to 3 is equal to number of variables, and therefore unique solution. If A not equal to plus minus 4, except these two values, given system has unique solution. Is it clear? For A equal to 4, system has infinite many solution. For A equal to minus 4, system has no solution, and for A not equal to plus minus 4, system has unique solution. We will take now next example. Same question in that second example. B, x plus 2y plus z is 2, 2x minus 2y plus 3z is 1 x plus 2y minus a square minus 3z is equal to A. So, augmented matrix AB is equal to, what is AB? Coefficient of x 1 to 1, y 2 minus 2 2, z 1 3 minus of a square minus 3 equal to 2 1 A. Now apply the operation R2 minus 2R1 R3 minus R1. This gives us 1 2 1 2, then 2 minus 2 is 0, minus 2 minus 4 minus 6, and 3 minus 2 3 minus 2, that is 1, and 1 minus 4 minus 3, then 0, 2 minus 2 0, this is minus a square minus plus 3 minus 1. So, we will get minus a square plus 3 minus 1 plus 2, and your a minus 2. So, now by using minus 1 by 6 R2, this entry will become, okay. So, this is 6 minus 6 minus 6 minus 6, we will get 1 there. So, you will take this as a row echelon form, okay. So, case 1, if minus a square plus 2 is 0, that is a equal to a square is 2, that is a is equal to plus minus root 2, then a minus 2 not equal to 0, and therefore rank A is 2 less than rank AB is equal to 3. Therefore, system is inconsistent. That is, it has no solution. It has no solution if A equal to plus minus root 2. A equal to plus minus root 2. Okay. Case 2, if A not equal to plus minus root 2, then minus a square plus 2 not equal to 0, and therefore rank A become rank AB is equal to 3 is equal to number of variables, and therefore system has unique solution. System has unique solution. If A not equal to plus minus root 2, plus minus root 2. Is it clear? And there is no case for infinitely many solution. For infinitely many solution, I want here to be 0, here to be 0, but that possibility is not there for any choice of A, and that's why infinitely many solution case is not there for any A. Okay. Next example. For what values of ABC the system is consistent? For what values of ABC system is consistent? Okay, in that B, x plus 3y plus z is A, minus x minus 2y plus z is equal to B, 3x plus 7y minus z is equal to C. Argumental matrix is coefficient of x 1 minus 1 3, 3 minus 2 7 y, z 1 1 minus 1 a b c constants. Now let us set to the equilibrium form r2 plus r1 r3 minus 3 r1. This gives us 1 3 1 a 0 minus 2 plus 3 gives us 1, then 1 plus 1 gives us 2, then here a plus b, okay, 3 minus 3 0, then 7 minus 9, okay, 7 minus 9 minus 2, then minus 1 minus 3 minus 4, right, and C minus 3A. Then from this we'll apply the operation R3 plus 2R2. This gives us 1 3 1 a 0 1 2 a plus b and 0 0 0, okay, this is now C minus 3a plus 2a plus 2b. So we'll get C minus a plus 2b. Okay, this is your row equivalent form. From R, system is consistent if and only if rank A is equal to 2 is equal to rank AB, if and only if C minus A plus 2B is equal to 0, if and only if A equal to say 2B plus C, A equal to 2B plus C, right. We'll take one more example of this type. Okay, I think it is not necessary to take that example. It is really too simple. Solve the following equations. One by x plus 2 by y minus 4 by z is 1, then 2 by x plus 3 by y plus 8 by z is 0. Next one is minus 1 by x, then 9 by y and plus 10 by z is equal to so this is not system of linear equations. Okay, here equations are not linear, equations are non-linear. Remember it. Substitute 1 by x is equal to say x prime, 1 by y is y prime and 1 by z is z prime say. Then we'll get x prime plus 2y prime minus 4z prime is 1, 2x prime plus 3y prime plus 8z prime is 0, minus x prime plus 9y prime plus 10z prime is 5. Now these are linear equations. We'll solve this for x dash, y dash, z dash by our usual technique, and then by either Gauss elimination, Gauss-Jordan elimination, we will get the values of x dash, y dash, z dash. Then your x is equal to 1 upon x dash, y equal to 1 upon y dash, z is equal to 1 upon z dash. Okay? Solve by Gauss elimination or Gauss-Jordan elimination. Gauss-Jordan elimination method to get x dash, y dash, z dash. Then x is equal to 1 upon x dash is equal to y equal to 1 upon y dash is equal to and z is equal to 1 upon z dash is equal to. So in this way we will obtain solutions of non-linear equations also. Non-linear equations, if by using some simple adjustment, if it is possible to convert given system to system of linear equation, then we can apply our Gauss elimination or Gauss-Jordan elimination method to solve that system of linear equations, and then what values we will get for new variables, and then by using the relation between old variables and new variables we can find solutions for old variables. So this is the technique to solve this example. So with this discussion we will stop this lecture here. Thanks for listening this lecture, and hereby our first chapter matrices and system of linear equations is all here. Bye bye.